Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we review everything you need to know about probability. So I've put on your screen all of the topics that I'm going to cover in this video. Let's start with the probability formula. So the probability formula is one that's very commonsensical. This is the formula. It says the probability of an event is the number of ways it can occur over the total number of outcomes. Note this NS means number in the sample space. The sample space is the list of outcomes. So you can only use this formula when all outcomes are equally likely. For example, you can't say, okay, I could get an A on my maths test or not get an A. So therefore, the probability of getting an A is a half. That doesn't work because getting an A and not getting an A are not equally likely events. You can only use this formula when all events are equally likely. So an example is if I roll a normal six-sided die. If I do that, all of the numbers 1 to 6 are equally likely to come up. So this notation here means the probability of getting a 6. Well, there's one way you can get a 6 because there's only one 6 on the die out of 6 outcomes in total. So note, when you're asked a probability, you should get a fraction. It's okay if you write it as a decimal, but your answer needs to be between 0 and 1. If I say, what is the probability of something? You need to give me a number between and including 0 and 1. The closer the probability to 1, the more likely that event is to occur. And the closer the probability to 0, the more unlikely it is to occur. So the probability of getting a 6 is only 1 over 6. That's close to 0, so it's unlikely to occur. There's not a good chance that you'll get a 6. All right, what would be the probability that I get an odd number? Note, here I use P and here I use PR, but they mean exactly the same thing. This just says the probability I get an odd number. Well, there are 3 ways this can occur. There are 3 odd numbers on the die, 1, 3, and 5. Out of 6 outcomes in total. So the probability you get an odd number is a half or 0.5. Again, it doesn't matter if you write it as a fraction or a decimal or even a percentage, but if you're asked probability, number needs to be between 0 and 1. So what's the probability I get an odd number or a 6? So this time there are 4 ways I can get this. I could get a 1, a 3, a 5, or a 6. 4 ways I can get it out of 6 in total, which just simplifies to 2/3. So what are we actually calculating here? Well, when we use this formula and we calculate the probability, we're actually calculating theoretical probability. This is the fraction of times we expect something to happen. So when I say the probability of getting a 6 is 1 over 6, I'm saying if I roll a die heaps of times, I would expect that I would roll a 6 1/6 of the time. So if I roll a die 150 times, I would expect that I would get 1/6 of those 150 rolls, which is equal to 25. I expect I would get that number of 6s. If I roll a die 150 times, I would expect to get 25 6s. I would expect to roll a 6 on 25 occasions because that is 1/6 of the total number of rolls. That's what probability is. I expect if I roll a die heaps of times, I would get an odd number or a 6 2/3 of the time, and I would get an odd number half the time. It's not necessarily what actually happens, it's just the fraction of times we expect something to happen. All right, let's move on to complements. So note the spelling here of complement. This E means that we're using complement as in goes together, not complement as in I give you a compliment for being an awesome math student. So we're talking about events that go together. So 2 events are complementary if they go together. The complement of an event is just the event not happening. So the complement of you going to school tomorrow is you don't go to school tomorrow. The complement of your team winning on the weekend is your team doesn't win on the weekend. So note this little dash here means not. So this formula just says the probability of not A is 1 minus the probability of A. The probability an event does not happen is just 1 minus the probability it does happen. So for example, if the probability it rains today is 0.7, the probability it does not rain is just 1 minus 0.7, which is 0.3. Note these two numbers add to 1. Probabilities add to 1 in exactly the same way percentages add to 100%. And we'll see later in the video, sometimes complementary events can make probability calculations much, much simpler. So let's move on now to sets. So a set is just a collection of objects. Could be a collection of numbers, collection of people, or whatever. So this symbol here, Greek letter epsilon, means universal set. So that just denotes the set from which we're going to take our objects. So in this example, I'm letting epsilon, the universal set, be the set of all integers between and including 1 and 20. So that means for this question, I'm just going to consider the numbers between including 1 and 20. My whole universe is just those numbers. I'm going to pretend numbers like 21 don't even exist. So what I'm going to do is write these two sets. First set A, set of even numbers, B, the set of multiples of 5. So when I'm writing a set, I need to use these squiggly brackets. That's just the mathematical notation for a set. So if A is the set of all even numbers, of course it's just 2, 4, 6, 8, but I'm only going to go up to 20. So this is the set A. I don't go past 20 because my universal set, I'm only considering numbers up to 20. So B, the set of multiples of 5. Once again, if I'm writing a set, I need squiggly brackets. So those multiples of 5, 10, 15, and 20. Again, I stop at 20 because my universal set only includes numbers up to 20. So here we're just going to learn a few symbols and some terminologies. So if I write something like this, the A in between these lines, this says the number in A. It's saying how many elements are in A. Each of these things is called an element. Each of the things that makes up set A is called an element of A. So in A, there are 10 things, there are 10 elements. So the number in A is 10. So the number in B is just 4 because there are only 4 elements in B. So we need to get two symbols really down pat. This symbol in the middle that looks like an N, the way you actually read it is AND. You read this as A and B. So A and B is another set, and this set contains everything that is in both. So A and B just contains things that are in A but also in B. So we wouldn't include 2 in the set A and B because 2's in A but it's not in B. The things that we would include are 10 because 10 occurs in both A and B, and also 20 occurs in both. So A and B is just a set with 2 elements, 10 and 20. So of course that would mean the number in A and B is just equal to 2. So that's A and B. Now the other symbol you need to know looks like a U. The way you read this is A or B. So A or B includes everything that's in A, everything that's in B, including everything that's in both. So A and B includes things that are in 2 of these sets. A or B includes any number that's in at least 1 of these sets. So it's going to be a much bigger set. So all of these numbers here are in A or B. All of these numbers are there, plus all of these numbers. Note, even though 10 occurred in both A and B, we don't write it twice. Similarly for 20, it occurred in A and B, but we don't write it twice. So that is the set A or B. So of course here the set not A, that would be just everything not included in A up to 20. That would be all the odd numbers. So 1, 3, 5, and so on all the way up to 19. So this would be the set A. It includes all the numbers between including 1 and 20 that were not in this list already. All right, let's move on now to Venn diagrams and two-way tables. So Venn diagrams and two-way tables are used when we're doing probability calculations involving two sets. What we use them for, both of them do exactly the same thing. They just display the information in an organized way to make probability calculations easier. So let's look at this question here. 200 year 8 students, 130 own a dog, 82 own a cat, 22 own neither, and we've got a few probabilities to calculate. So we're going to draw a Venn diagram and then a two-way table to display this information. So I know that I would use a Venn diagram or two-way table because this question involves two sets. Set of people who own a dog, that's the first set. Set of people who own a cat is the second set. So let's start by drawing a Venn diagram. So you always start with a rectangle in which there are two circles. So each of these two circles represents one of the sets. So we have a circle for the set of people who own a dog and the set of people who own a cat. So what we're going to do is we're going to put 4 numbers in here that correspond to the information that we've been given there. So you're probably thinking to yourself, well, hang on a minute, 130 plus 82 plus 22, that is way more than 200. In fact, 130 plus 82 plus 22 equals 234. So I've overcounted by 34. So how does that work? Well, the only way it could work is if I counted 34 people who own a dog a second time when I counted the people who own a cat. There must be 34 people in this set and also in that set. So however many you've overcounted goes in the center. I've overcounted by 34 because these three add to 234, when there are only 200 people. So the number I've overcounted goes in the middle. So now I look at this circle here. This is the circle of people who own a dog. So I already have 34 in this circle, but I need 130. So I need to put 96 more here. So there are now 130 in the dog circle. Similarly, I need 82 in the cat circle. I already have 34, so I need another 48 in that circle. The number that goes outside the circle are the people who own neither, in this case 22. So this Venn diagram is just displaying this information in a convenient way. So let's now draw up a two-way table. So a two-way table is actually a 4x4 table. Now there are two ways you can be. You can be in the dog set or not a dog owner. You can be in the cat owner set or not the cat owner set. So unlike for Venn diagrams, two-way tables have a row down here and a column over here for the total. But other than that, the information they display is going to be the exact same. So let's forget about the Venn diagram for a second. Let's just put this information in a two-way table. So firstly, it says there are 200 year 8 students. So put that number here. There are 200 people in total. So we're told 130 own a dog. So that means 130 people in total own a dog. So that number goes here. We don't put that number here because this is the cell for people who own a dog and a cat. It didn't say 130 people own both. It just said 130 people own a dog. Similarly, 82 people own a cat. So we'll put 82 there. And then it says 22 own neither. So the neither cell is this one here. It's in the not dog owners column and the not cat owners row. So where these two intersect, this means they don't have a dog and they don't have a cat. So we're going to put the 22 who own neither there. So we can figure out the rest of the numbers from the totals. So I know there are 200 people in total. So if 82 own a cat, that means 118 don't own a cat. If 130 own a dog, that means 70 don't own a dog. So the number that goes here, I say, what do I add to 22 to get 70? And that number is, of course, 48. The number that goes here, what do I add to 22 to get 118? That number is, of course, 96. And then this final number here, what do I add to 48 to get 82? And that's, of course, 34. So hopefully you notice that there is a very, very big similarity between the Venn diagram and the two-way table. These four numbers here in the two-way table are the exact same as the four numbers I have in the Venn diagram. So these two are both displaying the exact same information. We just have to know about both. So the whole reason for doing both of these was to make probability calculations easier. Now when I go to calculate each of these probabilities, it'll be so much easier. So the first one's saying probability of D and C. Probability someone owns a dog and a cat. Well, whether we use the Venn diagram or two-way table, we can see there are 34 who own both out of 200 in total. Once again, whether you write as a fraction or a decimal doesn't matter. So the next one says, what's the probability someone owns a dog or a cat? So D or C is everything in the circles. It's these three numbers here. These people own a dog or a cat, so do these, so do these. We include all the dog owners and all the cat owners. But just note, we don't include these people twice. So it's just 96 plus 34 plus 48, 96 plus 34 plus 48 over 200. So it turns out to be 178 over 200, or 0.89. All right, so this third one, let's read what it says. Probability of dog or not cat. This is the probability someone either owns a dog or does not own a cat. So let's go to our numbers here and see which of them satisfies this. So we would include all the people who own a dog and all the people who don't own a cat. We would actually include these three numbers, not this one. We include these 130 because they own a dog and these 22 because they do not own a cat. So adding all those up, we get 152 over 200. And again, it doesn't matter whether you write as a fraction or a decimal. All right. The final one says, what's the probability someone owns a dog and does not own a cat? Another way to say that is they own a dog but not a cat. They own a dog only. That means they're only in the D circle, not the cat circle. So that is just these 96 people here. In the two-way table, we're talking about these people here. We want all the people who own a dog but do not own a cat, which is them. I don't want to include those 34 because they do own a cat. So there are 96 people who own a dog but not a cat out of 200. And once again, I can write as a fraction or decimal. It doesn't matter. Okay, so that's all for Venn diagrams and two-way tables. Let's move on to mutually exclusive events. So two events are mutually exclusive if they prevent each other from happening. So mutual means they act on each other in the same way. Like if you and a girl both like each other, you say the feeling's mutual. Exclude means to stop something from happening. So mutually exclusive, they stop each other from happening. In other words, they cannot happen at the same time. So if I have two events, A and B, they are mutually exclusive if the probability they both happen is equal to 0. So let's just look at a few quick examples. So the event, I get an A in maths this semester and I get a B in maths this semester, they are mutually exclusive events. You can't have both happen at the same time. You can't get an A this semester and get a B. You can only have one of them. So that's why these two are mutually exclusive events. So in this next example, roll a die and get an even number, roll a die, get a number greater than 3. These events are not mutually exclusive. They are not mutually exclusive because they can both happen at the same time. I can roll a die and at the same time get an even number and a number greater than 3. I could get a 4 or a 6. If I get a 4, for example, I get an even number, and at the same time, I get a number greater than 3. That's why these two are not mutually exclusive. So why are we talking about this? Well, mutually exclusive events make probability a little easier. If two events are mutually exclusive, the probability that either of them happens, to find that out, you just add together the respective probabilities. So let's look at some examples. So for example, the probability I get an A in maths is 0.4. The probability I get a B is 0.5. What's the probability of an A or a B? So we already established in the previous slide that this event and this event are mutually exclusive. So the probability either of them happens, you just add together their two probabilities, and there you have it. 0.9 is the probability I get an A or a B. So let's look at a harder question. So it turns out if I were to toss a coin 4 times in a row, the probability I get no heads is 1 over 16, 1 head is a quarter, 2 heads is 3 over 8, 3 heads is also a quarter, 4 heads is 1 over 16. So don't worry about how I came up with these probabilities. You don't need to know them. I'm just telling you that. So we're going to find the probability that I get at least 2 heads. So why am I using this example? Well, apart from the fact that it's trickier, it involves mutually exclusive events. So the probability I get at least 2 heads is the same as saying I get 2 heads, or 3 heads, or 4 heads. Now, each of these events, 2, 3, and 4 heads, is mutually exclusive. If I toss a coin 4 times, I can't get 2 heads and also get 3 heads and also get 4 heads. It doesn't make sense. So, because these events are mutually exclusive, the probability this or this or this happens, I can just add together their probabilities. I can just add the probability of 2 heads to the probability of 3 heads to the probability of 4 heads. And that just gives me 11 over 16. So knowing about mutually exclusive events made this calculation so much simpler. All right, let's now move on to independent events. So 2 events are independent if they don't affect each other. What that means is they don't affect the chances. If one event does not affect the chances of the other happening, we say those 2 events are independent. So once again, knowing events are independent makes probability calculations that much simpler. So if I know 2 events are independent, the probability they both happen is probability A times probability B. So remember on the previous slide, we found out A or B. Now we're finding a formula for A and B. So AND questions involve multiplication and independent events. OR questions, which we did on the previous slides, they involved adding and mutually exclusive events. So let's look at how we could use independent events to make probability calculations simpler. So let's say I roll a die twice. What's the probability I roll 2 6s? So the probability I roll a 6 on the first roll is 1 over 6. The probability I get a 6 on the second roll is 1 over 6. Now these 2 rolls of the die are independent. It doesn't matter what you got the first time you roll the die. That does not affect what happens on the second roll of the die. So because these 2 events are independent, the probability they both happen, I get a 6 the first go, and on the second go, I just multiply together their probabilities, and I get 1 over 36. So now we have a harder question. I toss a coin 6 times. What's the probability I get at least 1 head? So the probability that I don't get any heads. So the probability I get a tail each time. This is the probability I get a tail the first go. This is the probability I get a tail the second go. I get a tail the third go, and so on. So the probability I get a tail all 6 times, I can figure that out using independent events. Each time I toss the coin is independent. It doesn't matter what I got the last time I tossed the coin. Each time I toss the coin, I have a 50% chance of getting heads, 50% chance of getting tails. So the probability I get a tail all 6 times, I can just multiply all of these together. So this is the probability that I get all tails or no heads. So, how do I figure out the probability I get at least one head? Well, I can use complementary events. This is the probability I get no heads. The probability I get at least one head is just 1 minus that. Because at least one head and no heads are complementary events. So not getting at least one head is the same as getting no heads. So I could put this straight on my calculator and I would actually get 63 over 64. That's the probability I get at least one head. So it's very close to 1. It's very, very likely I'll get at least one head. All right, let's now move on to our final topic of multi-stage events. So as the name suggests, multi-stage events involve events that occur in stages. It's when you're doing more than one thing. You could be, tossing 2 coins, rolling 2 die, tossing a coin and rolling a die, picking 2 cards from a deck. All of that occurs in stages. What we do is we use tables or tree diagrams. Now, they just give us a convenient visual way to list all of the possible outcomes. So just as Venn diagrams and two-way tables, they helped us visually with the number that were in each set. We use Venn diagrams and two-way tables when calculations involve 2 sets. We use tree diagrams or tables when the event involves 2 stages. Again, it's just a visual tool to help us with probability calculations. So let's say I roll a die and toss a coin. What's the probability I get heads or a multiple of 3? So what I'm doing is tossing a coin and rolling a die. I'm just going to use a table to list all of the possible outcomes. So across the top here, I am going to list all the outcomes I could get on the die, and down here I'm going to list all the outcomes I could get on the coin. So I'm just going to fill in this table with the outcomes. So I could get heads on the coin and a 1 on the die, heads and a 2, heads and a 3, and so on. I'll list all these outcomes. So here, these 12 things are my 12 possible outcomes. When you roll a die and toss a coin, there are 12 possible outcomes. So that makes our calculation easier. I want to find the probability that I get heads or a multiple of 3. So I can just go into all of these and circle the ones that satisfy what I'm after. So I get heads or a multiple of 3. So I'm going to circle all of these involving a heads, and then I'm going to circle all the ones involving a multiple of 3. So this one involves a multiple of 3. So does this one, and this one. So you can see there are 8 ways that I can get heads or a multiple of 3 out of 12 outcomes in total. And I'll just simplify that to 2 over 3. And that's our answer. Probability calculation, so much simpler because of the table. Let's look at an example now involving a tree diagram. So let's say I have a bag containing 4 lollipops, strawberry, cola, grape, and watermelon. And whoever gets the highest score in the test, they all get to pick 2 lollipops at the same time. So let's figure out the probability that they pick grape and cola. So this is not an easy question to do off the top of your head. What I'm going to do is list all of the possible outcomes to make it easier. But this time, to list all possible outcomes, I'm going to use a tree diagram. So if you pick 2 lollipops at the same time, you must have touched one of them first. So we can talk about the first lollipop. So the first lollipop you pick could be strawberry, cola, grape, or watermelon. So they're the 4 possibilities. So because I'm picking them at the same time, if you pick a strawberry the first go, you can't get a strawberry the second go. You can only get a cola, a grape, or a watermelon. Similarly, if I pick the cola the first go, I can only get strawberry, grape, or watermelon. I can't get a cola the second time around. So finishing off the tree diagram, I have this. So you're probably thinking, well, how does this mess actually help us? Well, we can list all of the possible outcomes by following the branches. So the first possible outcome is strawberry, then cola, so SC, and then I have SG, and so on. So all of these in black are the possible outcomes. That's why I did this, to get a list of the possible outcomes. So now I can see clearly there are 12 outcomes. Each of them is equally likely. So we can use that formula on the very first slide, in the very first example. The number of ways the event can occur of the total number of outcomes. So how many ways can the event occur? Well, I could get grape the first time, and then cola the second time. I could get cola first, then grape. There are 2 ways this event can occur out of 12 outcomes in total, and simplifying that, you get 1 over 6. So the probability you get a grape and a cola is 2 over 12 or 1 over 6. Again, this calculation made so much simpler because I listed all of the possible outcomes, and that was made easier with a tree diagram. Alright, sorry for the long video, but thank you so much for tuning in. Best of luck studying, but you're a superstar. You'll ace it. This has been the luckiest maths teacher in the world. Have a great day.